This conference will now be recorded.
Hello everyone. First we'll solve a problem and after that we'll start the chemical properties of alkene. That is, it is already started. We'll just continue the chemical properties of alkene and probably today we'll be able to finish it also. So in this question you can see one alcohol molecule is given. We have to find the total number of possible products, but not just any possible products that are formed from only tertiary carbocation. So from this alcohol, you can understand that this OH group is attached to this carbon. Now this carbon is attached to only two carbon. That means when you directly move OH group from this, we know that when it is formation of alkene, starting from this type of alcohol, and as the mechanism is undergoing through some carbocation intermediate, and that is the reason carbocation rearrangement is also possible. So when there will be carbocation rearrangement, you will see tertiary carbocation will also be formed. So only the product which is through tertiary carbocation, we have to consider those, not any other carbocation. Okay. So first, when we move this OH group, as the reaction is occurring in presence of acid, so OH group will be converted to OH2. So rest of the portion same. OH2, it is converted to OH2 plus because now one extra hydrogen is attached to oxygen. So oxygen is getting positive charge. Now it is becoming a very good leaving group. It will be removed from this carbon and there will be generation of a positive charge. So here you can see the generation of positive charge. Once in presence of H plus, this OH group is converted to good leaving group, which is H2 and then minus H2. That means water molecule is removed and you are getting positive charge over carbon, and this is 2° carbocation. Now if you look both sides of this carbocation, two types of migration possible. One migration is if the hydrogen from the right hand side, if it is shifted to this position with the electron pair, that means the two electrons that is present here, if hydrogen is taking both the electron, that means it will be now H minus. So this minus will be, this H minus will be attached to CH plus and new carbocation will be generated and the right hand side carbon. So this is the newly generated carbocation once this hydride is shifted. So this is formed by hydride shift from the right hand side. Suppose this is A. Another possibility is if methyl group is shifted from the left hand side carbon to this carbocation, in that case you will get positive charge on this left hand side carbon, isn't it? Now what is the purpose of this star sign? This is basically given to understand whether it is optically active or not, because it is asking total number of possible products. So we also have to consider if there is any possibility for enantiomer. But first we will see that these two are the carbocations, both are now 3°. That means from these the products that will be generated, you can count them as the answer. You should not count the alkene which will be formed from the first generated carbocation because that is 2°. We just have to consider tertiary carbocations, not secondary. So both are A and B, both are 3°. Now when it is A, if you look at the carbocation A, you will see the left hand side of the C plus and right hand side of the C plus. From both sides, hydrogen can be removed. That means there is a possibility of two types of alkene. So when you consider A, if the left hand side hydrogen is removed, that is as minus H plus, then without the electron, then you will get CC double bond. And if this right hand side hydrogen from this carbon is removed, you will get newly generated CC double bond at the left hand side of this carbocation. Now look at these two. Is there any chiral center? No, there is no chiral center present because this carbon is containing three similar groups. Here also this carbon containing three similar groups. So only two possibilities. Next you will see what about the B carbocation. Now when it is B carbocation, from both sides of this carbocation, it may be this hydrogen or any of these two methyl groups because both the methyl groups are equivalent. So when hydrogen is removed from any of these two methyl groups, you will get CC double bond generation is there at the left hand side. And if the hydrogen from this middle carbon is removed, you will get CC double bond like this. Now here, this is the chiral center, because with this carbon you have total 4 different types of groups. This is one group, this is another group, this is third group, and this is fourth group. So all the 4 groups are different. So that means if it is chiral, it will also have one more enantiomer, that is its enantiomer, its mirror image. But no chiral center is present in the other alkene, because this carbon is contained in 2 similar groups, so you cannot say that this is chiral center. And also here no question of cis trans, because with this CC double bond you have similar groups attached. See, similar groups attached. So that question, the question of geometrical isomerism doesn't arise. So in total you can see 4 different types of alkene, but out of these 4, only one alkene there is a chance of enantiomer generation. So that is the reason one more we have to add. So total 4 plus 1 because of this chiral alkene, and as a result total we will get 5. So this should be the correct answer, because it is mentioned total number of possible products. Next we will go to that is we will continue the chemical properties of alkenes. Remember, in chemical properties of alkenes there is total 3 main headings. The first heading, that is heading A, is addition reaction, and under the heading of addition reaction we have seen addition of different types of compounds. For example, addition of halogen, that is bromine, chlorine, addition of HX, that is HBr, HCl, then addition of water, that is the net addition of H and OH, then addition of HOX, that is HOBr or HOCl. So all these are examples under the common heading of addition reaction. Now the second one is B, which is oxidation. So under the heading of oxidation we will see different types of oxidation, what types of oxidizing agent you are using, what type of reaction condition you are using. Depending on that you will get different types of products. Fine. Now the first, under first oxidation reaction, we will see number 1, cold dilute. It must be cold, it must be dilute, neutral or alkaline, KMnO4 solution. We know KMnO4 solution, KMnO4 is very good oxidizing agent. Actually it is a very strong oxidizing agent, right? So obviously we can expect oxidation of the CC double bond. Now because of this presence of pi bonds, there is a tendency for alkenes to get readily oxidized by cold dilute, neutral or alkaline KMnO4. If you are thinking that what is the purpose of this cold dilute, neutral, alkaline KMnO4, why you are using like this, why it is not hot or why it is not concentrated, the reason behind that, if you use that kind of KMnO4, your product will be completely different, and that we will discuss once we finish this one. So it depends on the, suppose same reagent you are using, but how you are using the reagent, whether it is cold dilute, neutral solution, whether it is acidic solution or hot solution, everything matters. So that is why this heading is important. It is cold dilute, neutral or alkaline. It is not acidic in nature. So what will happen here? In presence of this type of KMnO4 solution, the pi bond will be broken, and in that place you will get 2 new OH group added to these 2 CC, that is 2 carbon atoms of the CC double bond. And this is called 1,2-diol, because the position of this 2 OH group, that is actually at 1 position and 2 position. Okay. So this is the reaction you can see here. We have taken the simplest alkene, we are treating it with KMnO4, cold alkaline, and we are getting 2 OH group attached. So here 1 pi bond, 1 sigma bond, pi bond will be broken, and we are getting 2 newly generated carbon oxygen bond. And this is position 1 and 2, and these type of positions are called, we call it vicinal diol or 1,2-diol. And what is the fate of KMnO4? It is itself reduced to manganese dioxide. Here the oxidation state of manganese is +7, but here it is +4. From the oxidation state you can understand it is reduced because it is oxidizing agent. So itself it will be reduced, right? So this is the fate of KMnO4. Now this reaction, there is an interesting phenomenon occurring here. it is having a very good color, very beautiful color, which is purple color. And you will see once the reaction is happening, the oxidation state is changed. Now KMnO4 is no longer present in the medium. You have only MnO2. So this purple space, which is the unique color of MnO4, this will be now it will be no longer there. So that means as the color is discharged, and there is you will also observe some brown precipitate because of this manganese dioxide. Though this brown is so dark, sometimes it appears as black, but actually it is very dark brown precipitate. So it is discharged, and in that place you get this type of brown precipitate of MnO2. So it means this type of visual change, it proves that reaction is happening. So now you can understand in this way, as there is a visual change, you can use it as a test for unsaturation. So suppose you have a compound, you do not know whether there is NCC double bond present or not, you just want to check. You can use KMnO4 solution. See, remember, same type of thing we have also seen in last class, we have discussed it, that when we add bromine water to CC double bond, then also the color is discharged. So those reagents where there is some specific color, and once the reaction is over, you cannot see the color anymore. Those tests you can use as identification test. Fine. So here also we can use it. In case suppose KMnO4 is not having any color, then it is not possible for us to understand whether actually reaction is happening or not. But because of this specific color, we can easily understand. So you can use this test for unsaturation detection, distinguish alkenes from alkanes, and it is also known by this name, that is Bayer's test. Fine. Some example with cyclic, and one more interesting thing also, just for extra information. Remember, there is another reagent that you can use, though for your syllabus it may not be there, but still, as it is giving you the same type of product, it is better to know about this reagent, which is osmium tetraoxide. And in this case, we have to use this extra reagent NaHSO3 in the second step, but product is same. And here you can see some stereochemistry is also there. So what it means, there is important information we can get from the stereochemistry, and that means here both the OH group are added from the same side of the CC double bond. So that is the reason both the OH group, they are on the same side, right? It is not like this, that while one OH is solid bond, another is dotted. It is not like that. Both are same side. So either you draw both with solid bond or with dotted line. So it will be Cs, because both the OH group are on the same side. And it is same also for if you take some open structure alkene, it is same. But another reagent is also there, which is giving you the same type of product, just like KMnO4. Okay. So whether it is cyclic CC double bond or open structure, you are getting dihydroxylated product. So that is why it is called dihydroxylation, because 2 times hydroxy group is attached. That is why the name is dihydroxylation. Fine. Now this is the direct product we are seeing here in this diagram, but what is the actual mechanism? If we see the mechanism, it will be clear. So again, we have taken cyclohexene, and here this MnO4 minus, this is MnO4 2 negative charge, sorry, 1 negative charge, because if you simply remove the potassium, there will be 1 negative charge present. So this MnO4 minus anion, it is written in this way, and then there is addition of these 2 OH group. As you can see from these arrows, green colored arrows, that there is generation of oxygen carbon bond, and that is from the same side. So because of this type of mechanism, it is easy for us to understand why it is both the OH group are on the same side, because it is syn addition. So this is the intermediate, but finally in presence, because in the medium you already have water, so these bonds will be broken, and in that place you will get 2 OH group. Now the same you can also do for open structure like this. So here also, as if this double bond is attacking this carbon, then this pi bond is attacking this oxygen, and there will be charge over Mn. So as you can see here, electrons are mentioned. So same type of mechanism, whether it is cyclic alkene you have taken or you have taken some open structure, it is same mechanism. Fine. But remember, it is syn addition. In case of bromine addition, remember there we have seen there is some generation of this type of halonium ion, and then in the second step the X minus is added from the opposite side. So that is actually anti, but in this case it is syn, right? And in that case also we have just remember, in case of bromination, what we have seen, when we have taken cis alkene, that means both the alkyl groups, similar alkyl groups are on the same side. Just take a simple butane. So it is 2-butene, that is cis-2-butene when they are on the both side. Now when it is already having groups on the same side and you are doing some anti-mechanism, then we have seen we are getting some pair of compounds, that is plus minus. We write it in this way. You are getting pair of enantiomers. And when it is trans, that means both the methyl groups are on the opposite side, and then again anti-mechanism. Now you are getting meso compound. But see, here the mechanism is syn, it is not anti-mechanism. Now what happens when the mechanism is syn? When the mechanism is seen and you have started with cis alkene, then what will happen? Now cis, syn, that is both are on the, it will have no effect. So you will get meso. So it is a easier way to remember. Sometimes it is very confusing, syn anti-addition. So you just have to understand this, that cis and syn, so you will get meso. And when it is trans and syn, that means these two are opposite. So you will again get pair of enantiomer. So as this mechanism is seen, so if you do it with the cis alkene, right, then you will get meso compound. And so now it is completely reverse. Whatever you have seen in case of halogenation, that is bromine addition, now you will see the reverse for cis and trans alkene. Some more examples we are going to see. So here we have taken propene. This is propene, right? Number 1 example, KMNO4. Cold NaOH, that means alkaline medium. Here one chiral center is generated, and as chiral center is generated, there is a chance that you will get another enantiomer, right? So 2 H groups are added to these 2 carbon. Now the second example is cyclohexene. Now this we have already seen, and now look at this one. This is trans. So when you have taken trans and there is some syn mechanism, you will get this. Obviously these two are on the added from the same side, but you will also get the enantiomer, right? So that I have just mentioned. But if you take cis like this and you are doing this using the same reaction condition, now you will get meso compound. Whatever you will get, you will see there will be a plane of symmetry, internal plane of symmetry plane, which is cutting the molecule into similar halves, and that is why it will be meso compound. Okay, so these are some examples for syn addition reaction by using cold dilute potassium permanganate. The next oxidation we are going to see now, it is hot KMNO4, and you will see now that the product is completely different. Now there is complete cleavage of CC bond. So this CC bond, double bond will be broken. So when you have some alkene, you are heating it with constant hot KMNO4 solution, and it is possible in whether you take it in basic or acidic. Mostly you will see, you will get question where it is mentioned as it is done under acidic condition. So complete cleavage of CC bond will take place, and there will be product formation. Different types of oxidation product you can get, and in general we cannot say what product, because that depends on the nature of the alkene. Now what it means? It means we have to take different types of alkene, and accordingly we have to understand the products. So first, suppose we have some terminal alkene. Terminal alkene means what? That means if you consider the CC double bond, one side there will be CH2 group attached. So any alkene you take, Forget about what is present on this side, but one side there will be always CH2. So if you have this type of alkene, you can call it terminal alkene. So when it is the case, then what happens? One of the product is always formic acid or methanoic acid. And formic acid, it will not, that is the reaction will not be stopped at that position. Further, it will be decomposed to CO2 and water. So if I take some general structure of terminal alkene like this, RCH-CH2, these are maybe methyl group, whatever, and you are using hot KMnO4, then what will happen? From this side, you will get RCOOH, and from the other side, you will get formic acid. So formic acid from one side and from the other side RCOOH, depending on our group, you can name it. If our group is methyl, it will be acetic acid. But it will not stop at this position. That is this is formic acid, right? But it will not stop at this position. Further, there will be oxidation because there will be in presence of oxygen atom, which is source is obviously KMnO4. What will happen? This HCOOH, it will be now converted to CO2 and water molecule. So one oxygen you require extra. If you break it like this, suppose this part is CO2, you need one more oxygen, and that is why I have written it in this way, which is obviously coming from KMnO4. So ultimately formic acid is converted to CO2 and H2. So it will happen when you have terminal alkene. But suppose if you do not have terminal alkene, you have some non-terminal alkene. Now non-terminal means what? Obviously now it is not CH2. It may be that both the H replaced by some RR group like this, or it may be only one hydrogen is replaced by some R group. So if you take this type of alkene, now you will get product ketones or carboxylic acid, or both of these products, that is both are carboxylic acid or both are ketone. That may vary because now you have two types. See, if you now consider the general mechanism, then what will happen? So from this side, that is, if I take any alkene like this, where one group is H, another one is R. Okay. Now you will get. So I'm not drawing the other part because there may be any possibilities there. So I'm just trying to see that whatever product will be there from this part, because from one part you will get one type of product, from another part we get another type of product. So for this case, from this side we will get product which is RCOOH. And if I take, this is type A, suppose this is type A, this is type B, and there may be anything. Now both are R group, two different types of R group, or it may be similar type of R group. Now we will get ketone because there is no CH bond, you have CR bond. Basically this CH bond is as if converted to COH, and from this part you are getting C double bond O. You can, it will, if you think it in this way, it will be easier for you to memorize. Okay, so C double bond O RR, and depending on what type of group is present on the other side, you may get the another pair of, that is the second product. So if you have suppose similar type of group like this, so what you will have, what will you will get? You will get another same molecule, right? And here also if you have R group and R prime, you will get another ketone, right? Or if you have here, suppose instead of R, if I am writing here H, then what will happen? From this side you will get some acid. So that is, it is mentioned there, you can get ketones or carboxylic acid or both of these products, and that depends on what type of alkene you have taken. So these are the general mechanism, but if we see want to see the actual mechanism, we can take example, simple example, that is the first member. So when you use hot KMnO4, what you get? You get 2 molecules of, from this side and this side, you get total 2 molecules of HCOOH. But the reaction will not be stopped here. Further, there will be decomposition of formic acid because you are heating it, and when you are heating it, it is not stable. It will be further decomposed to water molecule and H2O. Basically, 2 water molecule and 2 CO2 you will get. Then another terminal example, if we take, which is propene. Now from the left hand side, that is from this side, what you will get? You will get CH3COOH. And from the right hand side, you will get formic acid. But this formic acid, as we have said, in presence of oxygen, it will be converted to CO2 and H2. So ultimately, what you are getting from propene, you are getting acetic acid, carbon dioxide, and water. So these are the examples under terminal alkene. Number 1, number 2. When it is non-terminal alkene, now if we take example, suppose we have 2-butene. You are using hot KMNO4, whether it is acidic or basic, both possibilities are there. Now you will get, both sides you have similar type of groups, and here it is matching with this type, right? So you will get 2 molecules of acetic acid. Number 1 example. Second example, suppose you have total 4 methyl groups. So from this side and this side, total you will get 2 molecules of acetone. Third example. Now we have 2 different scenario both side. So from left hand side, again you will get acetone. And from the other side, you will get acetic acid. Okay. So these are the examples for non-terminal alkene. 2 types are there. Fine. Next reaction we will go, which is very important. Oxidation with ozone. Ozone means O3. Total 3 oxygen atoms are there. It is called ozone. And there is many steps. If you consider all the steps together, we call it ozonolysis. Okay. So what we do here, O3 gas is passed through a solution of alkene at a low temperature, and it oxidizes alkene first to ozonide. So this is the first step. So suppose you have taken some alkene, there may be, I'm not going into the details of the 4 substituent, it may be any substituent, just focus on the CC double bond. You are treating it with O3. First, you will get this type of compound, this type of cyclic structure you will get, and this is called ozonide. This is the first step. But this ring structure that you are seeing here, it is not very stable. So what will happen ultimately? There will be we will be going to use some other reagents, and ultimately this ring structure will be broken. Now ozonides are not very stable, and they are not isolated also, because it is not our desired product. So we do not isolate it, but it is a intermediate form. If you thoroughly examine the mechanism, its formation is there. But we do not isolate it because this is not the product that we want to make. So further steps are also there. What we do in the further step, in situ means in the same medium. Suppose the container where you are doing the reaction, in the same medium, once this step is over, next you add some zinc dust. Now this is reducing agent. So either you add zinc dust or you add some zinc dust in presence of water, obviously, or you use some H2PD. This is also another type of reducing agent, or you can use dimethyl sulfide, that is MESME. This is dimethyl sulfide. So all these are examples of reducing agent. You can use any of these. Mostly you will see zinc dust, water, or Me2S is used. These are common. And finally you get aldehyde or ketones. or mixture of these. Again, that depends on the structure of alkene. So what type of alkene you have taken, depending on that, you will get either aldehyde or you will get ketones. Fine. So what happens actually from this ring structure, though we will see the mechanism in the next slide, I am just saying right now that from this part, suppose there is some groups R or R prime. So from this part you get one product and from another side you get another product. Fine. So this is a two-step conversion process of an alkene, first into ozonite, followed by its reductive cleavage. Why we are calling it reductive cleavage? Because you are ultimately breaking this structure and you are doing it under reductive condition. So that is why you are calling it reductive cleavage to yield carbonyl compounds. And this whole process is known as ozonolysis. Remember, lysis means what? Lysis means to break something. You are breaking something. So you are breaking the CC double bonds ultimately. And you are doing it with the help of ozone. So that is why the overall term is ozonolysis. Now one more important point. Suppose you are not using in the final step, you are not using any reducing agent. You are simply using water to break this cyclic structure. Now what will happen? Your product will be different because this reducing agent, it matters. If you are not using it, what will happen? If the ozonides are decomposed only with water without using any reducing agent, the H2O2 produced during the reaction, because if you thoroughly examine the mechanism, there is formation of the side product H2O2. Now this H2O2, it can act as oxidizing agent and it can oxidize the initially formed aldehyde to corresponding acid. So suppose there is formation of aldehyde from this side, though when you have two R groups, it is not like that. When you have one H and one R, then aldehyde will be formed. So suppose aldehyde is formed, but you will not be able to isolate it because what will happen, as you are not using any reducing agent, the H2O2, which is the side product here, it will be oxidizing this aldehyde and ultimately it will be converted to acid. So instead of getting aldehyde, you will end up with acid. So this is the problem we face if we are not using any reducing agent. But if our purpose is to make it, then it's okay. But if we want to make aldehyde, we have to use reducing agent. The reaction is highly useful in detecting the position of CC double bond in alkene. Now see, when you have very complex or large structure of alkene. So for example, suppose there is a long chain. Now the double bond can be here, the double bond can be here. That is, the double bond can be at 2 position. Then the double bond can be at this 5 position, but you do not know. Now in this case, you can use this reaction to detect, for detection purpose, because when you use this reaction, the CC bonds will be cleavage, will be broken. Now from the product that you will get, because if it is broken here, from this side you will get acetaldehyde, and from this side you will get some large structure carbonyl compound. Similarly, if both the double bonds are present at 2 and 5, what will happen? It will not just break here, it will also break here. So product will be different. Now if you consider all the 4 products, and if there is only one double bond, you will get 2 products because there is only one time cleavage of this CC double bond. So from the product that you will get, that is experimentally whatever you will get, from this you will be able to understand what is the position of double bond. Because if you are suspecting the double bond is at 2 and 3 position, then obviously you can predict the product. And if you are getting the same product, that means yes, your assumption is right. Okay. So in this way, it can be used for detection purpose of the location of CC double bond. Now we will see some examples. Here, when you start from this type of alkene and it is broken here, so from the right hand side you will get, just in this C double bond C, you just have to put oxygen and you will get your product. So if you put oxygen, you get what? You get formaldehyde, which is ACHO. And from the other side, just add 1 C double bond O in place of CC double. So you get this type of aldehyde. Now aldehyde you will get if you are using in the second step any of these reducing agent. But if you are not using it, what will happen? You will end up with the corresponding acid. It will be converted to the acid, that is propanoic acid. It will be converted to formic acid. So just look at the reagent, whatever is given in the question, whether it is reducing agent mentioned or not. Mostly reducing agent will be mentioned, but this extra information is also very important. If reducing agent is not mentioned, product will be different. Then in the second example, this is both sides we are having same type of group, so that is why two molecules both are same. Then again symmetrical type of structure, so from both sides you will get acetone. This side, both sides same molecules. Now look at the mechanism. Though detailed mechanism for this level is not necessary, but in case you are interested, see this ozonite you have seen in the previous slide. So what we have done, directly from this starting material, directly we jump to this step. But here you have some steps, that is step 1, step 2, step 3. From this come here, then step 3, and this is the fourth step. But here that is in the previous slide, what we have seen directly we have jumped to ozonite, and then from ozonite you are getting a final product. But in between many things are happening. See, O3 addition to alkene, first you are these OC bonds are formed, you are getting, this is another cyclic structure, but don't be think these are same as ozonite, because ozonite is different. You can understand here 3 oxygen 1 by 1 side by side, so it is called molozonite. Then this is fragmented, just follow the green arrow, it will be helping you to understand what type of fragments you are getting. Now the same fragments, again it is written here, fragments now recombine to form ozonite. Now when it is recombining, see, now this oxygen, its direction is now towards this carbon. So that is why, as if this carbon and oxygen is connected, and this oxygen is connected with this, and you are getting ozonite. And finally, in presence of Me2S, we are getting from this side, that is carbon with 2 substituents, carbon with 2 substituents, it is general structure. There may be any substituent. So it is reduction by Me2S or any other reducing agent. Now some examples we will see. Here we have taken alkene. In the left hand side, we have this 3 carbon chain and 1 methyl group. And the other side we have methyl group and we have hydrogen. In presence of O3 Me2S, this 4-5 bond broken, and what will happen, just from the numbering you can understand that is which carbon is this 4 carbon originally. This is as we have 2 R groups attached, so we are getting ketone, and in the right hand side we have 1 H 1 R group, so we are getting aldehyde. Okay, here what is the difference with the previous one? In number 1 we have this side is again same, so again you are getting same product, these two are same, isn't it? But now both are hydrogen, so you will get formaldehyde. Next example, now we have taken some ring structure. CC double bond is part of the ring, and there is also 2 methyl substituent at 3 and 6 position. If you are breaking it in this this CC double bond, now the structure will open. And for cyclic alkene also, if you want to detect the position of double bond, this is a very helpful reaction, because just move backward. If you connect these two positions, 5 and 1, basically you get, sorry, not 5 and 1, 6 and 1, 6 carbon and 1 carbon. If you connect, you get the ring structure. Fine. So from the product also we can understand what is the position of double bond, because if the double bond is located here, suppose at 4-5 position, then obviously your product is different, right? So you may get question like this, suppose the product is given and in the options 1, 2, 3, 4, you several ring structure with, that is cyclic alkenes are given, so you have to recognize which one will be the starting material just from the product. So this type of question may be framed. Fine, just for example I'm saying this. So 3 examples. for ozonolysis. Next oxidation is oxidation with directly we are using oxygen, or you can call it air combustion. That means you are doing some combustion reaction, and combustion reaction is a reaction of hydrocarbon. It may be alkane also, but now we are discussing alkenes, so obviously we will see examples with alkenes. So alkenes can undergo complete combustion or incomplete combustion. Now complete or incomplete, that depends on the how much oxygen you are supplying. Now one important point is here, because of higher carbon hydrogen ratio of alkene, if you compare with alkane, the ratio of carbon and hydrogen, and here the ratio of carbon and hydrogen is different. Now the tendency for incomplete combustion, it is high, producing a smoky flame in air. Now this type of smoky flame we do not get in case of alkanes. We get it only when there is the chance of incomplete combustion, because when there is incomplete combustion, the product CO2 we do not obtain. Instead, carbon can be obtained. Now carbon is the source of soot formation, which is creating this type of smoky flame. So if the flame is smoky in nature, that is sooty in nature, then it can indicate that it is incomplete combustion. Okay. So complete combustion occurs when there is excess oxygen forming water and CO2. Now excess oxygen means that enough oxygen must be there, so that just consider it the formula C2H4. Now when you have taken 1 mole of C2H4, obviously you should get, sorry, here should be 2, not 4. So if it is 2, now C2H4, so obviously number of moles of CO2, it should be 2 moles of CO2, and total hydrogen is 4. That means it must be 2 water molecules, because per water molecule 2 hydrogen atoms are there. So 2H2 or 2 CO2. Now in 2 CO2 you have total 4 oxygen, and here you have 2 oxygen. So total oxygen is 6. So that means it must be 3. So 3 O2. Now when we are having this type of excess, that is enough oxygen present, though this is a balanced equation, but even if you supply enough oxygen, obviously according to balanced equation you will write the equation, but some extra oxygen can be left. So when we are using excess oxygen, we are getting this product. And if I keep it as it is, suppose if I am already maintaining it is a 644, then you have to add here, just make it double. It should be 2 moles of C2H4. But if it is 1 mole, it should be 3 O2, 2 CO2, 2 H2. Now this is complete combustion, but if we have incomplete combustion, when it will happen? When there is not enough oxygen to burn. So you will get some mixture of products. Now look at these products, what difference we are having here. So C2H4, suppose we have 4 CO2, so 4, so this will be 2. Now if it is 2 CO and 2 H2O, so total number of oxygen is 4. So when we are supplying per mole of C2H4, when we are supplying 2 moles of O2, but actually you should supply for complete combustion 3 moles of O2. The ratio is 1:3. But suppose you are supplying 1:2, then what will happen? You will end up with not CO2 but CO. Water is always there, but we are not getting CO2. So this is the incomplete combustion. Another possibility is there when there is, this is 2, this is 2. So total number of oxygen is O2. Now look at the ratio. In this case, it is 1:2, but now it is 1:1 oxygen. That is mole ratio is 1:1. When you are supplying oxygen so less that it is even lesser than the previous one. Now even you are getting CO. Now you are getting carbon only. So there is a soot formation, carbon or soot, and this probability of incomplete combustion, this is more likely to occur in higher alkenes where there is large number of carbons present. Then this chance is high and the flame is sooty yellow nature. So this is number 4, oxygen under oxidation. This is number 4 reaction. Now come to number 5, which is oxidation with oxygen, but there is some silver catalyst. It is not directly we are using oxygen. There is some catalyst. In presence of silver catalyst, or it may be Ag2O. So either you take directly Ag2O or you can take mixture of this. This is the temperature. There will be formation of epoxy alkane or epoxide. If this is alkene, you are using this reagent, you will end up with structure like this. So this is epoxide or epoxy alkane, and the sigma bond is still present. So that is, it is mentioned here without the cleavage of sigma bond. So here only the pi bond is broken, sigma bond is still there. Further, if you do some acidic hydrolysis of this epoxide, that will lead to formation of 1,2-diol. Remember, this type of product we have seen when we have used cold dilute KMnO4, same type of product you will get, but you have to do this extra step, which is acidic hydrolysis. This is number 5. Now under oxidation we have finished all the reactions. Now we have reached C, which is polymerization. So addition done, oxidation done. Number 3 is polymerization. Polymerization is a process in which large number of simple and small molecules that are called monomer. So this is basically the definition of any polymerization, not just with alkene. Polymerization is formation of very large structure, but starting with some simple small molecule. Ultimately, you will get some large molecule, which we call polymer. But polymer is combination of several simple and small molecules, and these small units are called monomers. Now, for alkenes also, this type of polymerization is very common. You will not get it in alkane. It is only for alkene at high temperature and pressure, and there is also catalyst. Now, under polymerization, first we will see polymerization of ethene. Now, details of polymerization, what happens, what kind, that is different depending on what type of alkene you have started with. Details is, there is separate unit for it, polymerization. But here we will just see 2 examples. One is with ethene. So, ethene means the first, the simplest alkene, that is ethylene or ethene, heated to 473 Kelvin under a pressure of 1500 atmosphere. So look at the value, it is so high. In presence of a trace amount of O2, it undergoes polymerization and we get polyethene. So here you can see we have taken n number of ethylene molecule and we are getting this type of polyethene. So how you are getting the name polyethene? Poly, that is many ethene. So that is why the name, just connect it together, polyethene. And n number. So this unit within third bracket, that will be repeated both side. It will be repeated. So that is, it is written in this. It is widely used as packaging materials, squeeze bottles, refrigerator, tray, pipes, radio, TV cabinet. So these are the applications of this polyethene. If you use propene as starting material, that is also alkene. This is temperature. Now the pressure is comparatively less. In presence of trace of benzoyl peroxide. So we are using some oxide. Benzoyl peroxide is PHCO OCOPH. As radical initiator, because the mechanism is through radical and this pi bond is broken, there is radical generation. And now you can understand why it is not happening with alkane, because in alkane this radical generation is difficult. Here we have pi bond, so it can occur easily. And here we are using this special catalyst called Ziegler-Natta catalyst. Just look at this combination, because if you are getting question that what is Ziegler-Natta catalyst, suppose in options you will get different combination of compounds. So just recognize it. TiCl4 and triethyl aluminium. So in presence of this catalyst and all these reaction conditions when we are maintaining, we get the polymerization of propane. So n number of propane we are taking and we are getting polypropene N. So this unit will be repeated again and again in the polymer. It is harder and stronger than polythene, and that is why now its application is a little different. Okay, so look at this seat cover, ropes, plastic bucket. Obviously these are harder and stronger than these previous examples, right? Here we have a question. Butene on reaction with alkaline KMnO4. Now not just alkaline KMnO4 is enough, you have to understand this reaction condition followed by acidification. Now what is this purpose of acidification? That also we have to understand. Look at the options. Here it is saying the first option, it is one aldehyde molecule, one acetic acid. Second option is saying that two acetic acid molecule. The third option is saying this type of 1,2-diol. And the last option is saying that both are aldehyde. First draw the structure. Butene is 4 carbon. Now here this is, remember the type, this is this type where you have one H and one R. So when it occurs, what we get? We get, just have a look here so that it is completely clear. So see, non-terminal alkene, that is CHR. So when we have this type of molecule where you have one side C and H and R, we get acid. So obviously it will be CH3COH, but if you are thinking what is the purpose of using CH3, that is acidification, just let me tell you that you are doing this reaction first of all alkaline KMnO4. That means in the medium you have some hydroxide ion. So when you will get the acid from both sides, you will get it in the form of O minus, and depending on you have taken NaOH or KOH, it will be in the salt form. Once you do acidification, finally it will be converted to acetic acid. So that is the purpose of using the second step, which is acidification, right? So 2 molecules of acetic acid you will get. Option 2 will be the correct option. Next question. 2 isomers A and B. Molecular formula is C4H8. Give different products on oxidation with KMnO4, and now we are doing it in acidic medium. Now whether you are heating it or not, that is not mentioned, but remember when it is cold dilute, it is always alkaline, but here it is mentioned acidic. So even if it is not mentioned that it is you are heating it or not, you can consider it that condition. That is a second oxidation type where we have seen it with hot KMnO4 that in both acidic or basic medium. So isomer A on reaction with KMnO4 acidic medium results in effervescence of a gas. So this is a very important indication. Effervescence of a gas means what? Remember, when formic acid is produced, this formic acid is ultimately converted to CO2 and H2O. That means there is a chance that formic acid will be produced. Effervescence of a gas and it gives ketone. So what will be the compound A? First one is mentioned as but1ene. Now but1ene is this one. Now the second one is cis-but2ene. This is trans-but2ene and this is 2-methyl-propene. Now look at this. It is giving you effervescence of gas. That means there is a chance of formation of formic acid, and it is also giving you some ketone. So from one side you should get ketone, from another side you should get formic acid, and that is possible only with 2-methyl-propene, isn't it? Because if you are breaking it from this side, that is CH2 side, you will get the formic acid, and from this side you will get acetone. But that is not possible in any other options. Because if you are doing it with the first one, from this side you will not get as ketone, you will get aldehyde. right? Sorry, you will get acid, and from this side you will get formic acid. So effervescence of gas is fine, but you are not getting ketone. And the same problem is also with this. You will not get ketone. You can get ketone, also CO2 gas, only with the last option. So that is why this is the correct option. Second question also you will find some similarity. It is also saying that an organic compound A, C4H8 again, KMnO4H plus yields compounds B, C3H6O. So whether it is ketone, directly it is not mentioned, ketone, aldehyde, whatever, but it is not acid because you have only one oxygen. And yields compound B, so this is the product. Compound A also yields compounds B on ozonolysis. So this is a combination of two questions, right? So you have to apply the knowledge of both ozonolysis as well as this KNO4 oxidation. So from A, you are getting B when you are using KMnO4 acidic condition, and you are getting ozonolysis. Ozonolysis means both the steps followed by reducing agent. Reducing agent, again you are getting B. So we know that when it is ozonolysis and you are getting C3H6O. Now C3H6O, what type of structure there may be? It may be acetone. Is there any other possibility? Suppose if I am drawing it like aldehyde, then one more carbon, 1, 2, 3. So if I am saying this, then what is happening? 2-methyl propene, this is one option. Then 1-methyl cyclopropane. Now it is propane, cyclopropane. It is obviously it will not correct answer. In structure must be there because you are doing ozonolysis. So but 2-in. Trans is not mentioned. But if it is but 2-in, what you will get? You will get from this side this structure, which is acetaldehyde. And here you do not have C3H6O because it is only 2 carbon. From this side also you are getting this. So it is obviously not C3H6O. Fine. Okay. And if it is 2-methyl propene structure like this, and if you are doing it, if you are doing treating it with KMnO4H plus, what we get? We have already seen from one side we get acetone, from other side we get formic acid, which is ultimately leading to H2O and CO2. But if you are doing ozonolysis, what you get? From one side you get acetone, from other side you get formaldehyde. But in both times you are getting acetone, which is basically C3H6O. So only in this case 2-methyl propene, both the conditions are fulfilled. So that is why this should be the correct answer. Okay. So we will end the session here. Thank you for listening.